We shall now discuss on module 3 of chapter 8. Module 3 is concerned with the convergence of a sequence of elements and convergence of a sequence of bounded linear operators. Here convergence of a sequence, namely strong convergence, weak convergence of a sequence, and also strong convergence, non-convergence, weak convergence of a sequence of bounded linear operators. Also we shall study on some properties of sequences of operators and sequences of elements on an underlying nonlinear space. Let us now start the slide presentation of module 3 of chapter 8. Let us now start module 3. The title of module 3 is strong convergence and weak convergence of a sequence of operators. Let us take some definitions. A sequence xn in a nonlinear space capital X over a field capital K is said to be weakly convergent to an element x belongs to capital X if for every f belongs to x star, that means for every functionals f, fxn goes to fx as n tends to infinity and written as xn goes to x weakly. Let us take another definition. A sequence xn in a nonlinear space capital X over a field capital K is said to be strongly convergent to an element x belongs to capital X if norm xn minus x tends to 0 as n tends to infinity and written as xn goes to x strongly. Let us take a theorem in this regard. If a sequence elements xn belongs to capital X such that xn converges to x weakly and x belongs to capital X, then the weak limit x of sequence xn is unique. Every subsequence of sequence xn in capital X is convergent weakly to small x. And number 3, the sequence of norm xn is norm bounded. Now we shall take the proof one by one. Let xn converges to x weakly and xn converges to y weakly belongs to capital X where x is not equal to y. Now x minus y is not equal to 0 vector. So by application of Hahn-Banach theorem, there exists a functional f belongs to x star such that f of x minus y is equal to norm x minus y with norm f equal to 1. Since xn converges to x weakly and xn converges to y weakly for every f belonging to x star, fxn converges to fx and fxn converges to fy as n tends to infinity. As the field of scalars is Hausdorff, we see that fx equal to fy. So f of x minus y equal to 0, that means norm x minus y equal to 0 imply x equal to y, which is a contradiction to our assumption. Hence the weak limit x of sequence xn is unique. Now we shall give a proof of 2. As xn converges to x weakly, then for every f belonging to x star, fxn converges to fx as n tends to infinity. So every subsequence of sequence fxn is convergent and converges to fx. Let fxnk be a subsequence of sequence fxn. So fxnk converges to fx as k tends to infinity. That means xnk converges to x weakly. Now we shall give a proof of 3. As xn converges to x weakly, for every f belonging to x star, fxn converges to fx as n tends to infinity. So modulus of fxn less or equals to m suffix small f for some constant mf greater than 0, because every convergent sequence is bounded. Let capital C from capital X to x double star be a canonical mapping defined by Cx equal to capital Fx, where capital Fx belongs to x double star satisfying norm Fx equal to norm x. So for every f belongs to x star, we have Fxf equal to Fx. Take a sequence of functionals Gn belonging to x double star such that Gnf equal to Fxn. So modulus of Gnf less or equals to mf, that is modulus of Gnf less or equals to m suffix small f for every f belongs to x star. As x star is complete and sequence Gnf over capital X star is a bounded sequence of scalars, so by uniform boundedness principle norm Gn is bounded, but norm Gn equal to norm Xn, so sequence norm Xn is bounded and hence the proof is complete.
Let us take another theorem. Let capital X be a nonlinear space, then the following statements holds. That means strong convergence implies weak convergence of a sequence in capital X. Number 2, if dimension of X is finite, then weak convergence and strong convergence of a sequence in X coincide. Now let us take a proof. Let sequence Xn be a sequence in capital X and let Xn converges to X strongly and X belongs to capital X. Let F belongs to X star. Now modulus of Fxn minus Fx equal to mod F of Xn minus X, because F is linear. As F is bounded, so modulus of F of Xn minus X less or equals to norm F into norm Xn minus X, which goes to 0 as n tends to infinity. This is true for all F belongs to X star, hence Xn converges to X weakly. But the converse is not true. Let us take an example. X is equal to sequence space L2. So its conjugate space X star is equal to L2. Let Ek, where k equal to 1, 2 and so on, be a Soder basis of capital X, where Ek equal to 0, 0, 1, where 1 is in the kth place, comma 0, comma 0 dot dot dot. Let X belongs to L2, where X equal to sequence of elements Ch1, Ch2 dot dot Cn, comma dot dot dot, with norm of X equal to sigma I equal to 1 to infinity modulus of Chi square to the power half, which is less than infinity. Take X belongs to L2, then X equal to sigma I equal to 1 to infinity alpha k Ek, where alpha k's are scalars. Let F belongs to X star, so F of X equal to F of sigma k equal to 1 to infinity alpha k Ek, which is equal to sigma k equal to 1 to infinity alpha k F of Ek by applying the linearity of F, which is again equals to sigma k equal to 1 to infinity alpha k gamma k, where gamma k equal to F of Ek. Note that gamma k belongs to L2, that means the sequence of scalars gamma 1, gamma 2 dot dot gamma n dot 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 belongs to L2, where sigma k equal to 1 to infinity modulus of gamma k square is finite. So gamma k tends to 0 as k tends to infinity. So F of Ek goes to 0 as k tends to infinity. This means F of Ek goes to F0 because F0 equal to 0 as k tends to infinity, which implies that Ek converges to 0 vector weakly. For any two positive integers n and m with n not equal to m, we see that norm of En minus Ems square equal to 2, which implies that norm of En minus Em equal to root 2, which is greater than 0. So sequence En is not a Cauchy sequence in capital X, hence En does not converges to 0 vector strongly. Let us take a remark. In an infinite dimensional nonlinear space capital X, weak convergence of a sequence in capital X does not necessarily imply its strong convergence. Note that strong convergence of a sequence in a nonlinear space implies its weak convergence. Since dimension of X is finite, say dimension of X equal to k, take E1, E2, dot 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 Ek be a basis vectors of capital X. Let Xn belonging to capital X and X belongs to capital X such that Xn equal to alpha 1n E1 plus alpha 2n E2 plus dot 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 plus alpha kn Ek, and X equal to alpha 1 E1 plus alpha 2 E2 plus dot 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 plus alpha k Ek. Let F1, F2, dot dot Fn belongs to X star such that Fj En equal to 0 if j not equal to n, Fj En equal to 1 if j equal to n. So Fj Xn is equal to alpha Jn and Fjx equal to alpha j. Let Xn converges to X weakly. So Fj Xn converges to Fjx as n tends to infinity for j equal to 1, 2 up to k. This implies that alpha Jn goes to alpha j as n tends to infinity. Let capital M is equal to max of norm Ej, where j is taken from 1 to n. Let epsilon greater than 0 be arbitrary. So there exists a positive integer n belongs to set of natural numbers such that modulus of alpha Jn minus alpha j less than epsilon by m into small k for all n greater or equals to capital N and for each j equal to 1, 2 up to k. Now norm xn minus x equal to norm sigma j equal to 1 to k alpha j n ej minus sigma j equal to 1 to k alpha j ej, which is equal to norm sigma j equal to 1 to k alpha j n minus alpha j into ej, which is less or equals to sigma j equal to 1 to k norm alpha j n minus alpha j into ej, which is equal to sigma j equal to 1 to k modulus of alpha j n minus alpha j into norm ej, which is less than small k into epsilon by m into small k into capital M, which is equal to epsilon for all n greater or equals to capital N. This implies xn converges to x strongly. Let us take definition in respect of bounded linear functionals. Let capital X be a norm linear space and let Fn be a sequence of bounded linear functionals belonging to X star, where X star being the conjugate space of capital X. Take F naught belongs to X dashed, then Fn converges to F naught weakly if for all x belongs to capital X, Fn x converges to F naught x in norm. Now in this connection we take a theorem. If Fn converges to F naught weakly, then sequence of norm Fn is bounded. Let us take another theorem. Let sequence Fn belongs to X dashed be such that Fn converges to F weakly where F belongs to X dash, then sequence norm Fn is bounded. Number 2, Fnx converges to Fx for arbitrary x belonging to a subset G of capital X, for which the linear combination of its elements are everywhere dense in capital X, and conversely if 1 and 2 holds, then Fn converges to F weakly. Let us take a proof. If Fn converges to F weakly, then 1 follows from previous theorem and 2 follows from the definitions. Let 1 and 2 holds. Let x belongs to capital X, let epsilon greater than 0 be arbitrary. Choose x naught belongs to capital G such that norm x minus x naught is strictly less than epsilon by 2. Now modulus of Fnx minus Fx equal to modulus of Fnx minus Fnx naught plus Fnx naught minus Fx naught plus Fx naught minus Fx, just slight adjustment of Fnx naught and Fx naught, which is less or equals to modulus of Fnx minus Fnx naught plus modulus of Fnx naught minus Fx naught plus modulus of Fx naught minus Fx. This is equation number 1. As sequence norm Fn is bounded, there exists a constant capital M greater than 0 such that norm Fn less or equals to capital M for all n. Also modulus of Fnx naught minus Fx naught goes to 0 as n tends to infinity by the assumption 2. So from equation 1 we have modulus of Fnx minus Fx less or equals to norm Fn into norm x minus x naught plus modulus of Fnx naught minus Fx naught plus norm F into norm x naught minus x, which is less or equals to m into epsilon by 2 plus 0 plus norm F into epsilon by 2 as n tends to infinity, which is again equals to capital M into epsilon by 2 plus norm F into epsilon by 2. As epsilon greater than 0 is arbitrary, it follows that Fnx converges to Fx for all x belongs to capital X, implying that Fn converges to F weakly. We take another theorem. Let capital X be a separable Banach space, then every bounded sequence of functionals Fn belonging to X dash contains a weakly convergent subsequence of sequence Fn. Let us take a proof. As sequence of functionals Fn belongs to X dashed are bounded, without loss of generality we can take norm Fn less or equals to 1 for all n. Let capital E equal to sequence x1, x2, dot 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 xn, dot dot be a countable set in capital X which is everywhere dense in capital X. Now sequence Fn x1 is bounded sequence of scalars. So sequence Fn x1 has a convergent subsequence, say f11 x1, f21 x1, dot dot fn1 x1, dot dot dot. Select the sequence f11, f21, f31, dot dot fn1, dot 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 of fn such that sequence Fn1 x2 is a bounded sequence of scalars. So by similar argument, sequence Fn1 x2 has a convergent subsequence, say f12 x2 comma f2 x2 x2 comma dot dot fn2 x2 comma dot 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 dot. This follows that every bounded sequence has a convergent subsequence. Again, sequence of functionals f12 comma f22 comma dot 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 fn2 is a subsequence of sequence fn1 and hence is a subsequence of sequence fn, and this process can be continued. Continuing in this way, we can get a subsequence f1n xn comma f2n xn comma dot 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 fnn xn comma dot 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 of the earlier subsequence f1n minus 1 xn comma f2n minus 1 xn comma dot dot fn n minus 1 xn comma dot dot dot. Thus, we get a subsequence of sequence fn like f11 f21 dot 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 fn1 dot 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 f12 f22 dot 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 fn2 dot dot dot. Continuing in this way, we get f1n comma f2n comma dot dot fnn comma dot 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 and so on. Consider the diagonal elements f11 f22 dot 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 fnn where each of its elements are convergent at each xk, k equal to 1, 2 and so on. Let x belongs to capital X. Choose xk belongs to capital E such that for every epsilon greater than 0 there exists a positive integer n such that norm of x minus xk less than epsilon by 3 for all n greater or equals to capital N. Now for n equal to 1, 2, dot dot modulus of fnn xk minus fnn x equal to modulus of fnn xk minus x less or equals to norm fnn into norm xk minus x, which is less or equals to norm xk minus x, which is less than epsilon by 3 for all k greater or equals to n, since norm fnn less or equals to 1. Now modulus of fnn x minus fmm x less or equals to modulus of fnn x minus fnn xk plus modulus of fnn xk minus fmm xk plus fmm xk minus fmm x with mod. Now sequence of functionals fnn xk is convergent and hence fnn xk is a Cauchy sequence of scalars. So for epsilon greater than 0 there exists a positive integer n1 such that modulus of fnn xk minus fm xk is strictly less than epsilon by 3 whenever n comma m is greater or equals to capital N1. Choose n not equal to max of capital N comma n1. So from equation 3 we get modulus of fnn x minus fmm x is strictly less than epsilon for all n comma m greater or equals to n naught, showing that sequence fnn x is a Cauchy sequence of scalars, and since scalar field is complete, let fnn x goes to alpha, say for x belongs to capital X. Define a function g from x to k, k being the field of scalars such that gx equal to alpha for x belongs to capital X. So fnn x goes to gx where gx equal to limit n of fnn x. Clearly g belongs to x star, and this follows that fnn goes to g weakly. This completes the proof.
Up to this, in this module, we have learned so many properties on convergence of a sequence of elements on a nonlinear space. Now we shall discuss on convergence of a sequence of bounded linear operators. We shall define strong convergence, non-convergence, uniform convergence of a sequence of bounded linear operators, and we shall study on such convergence of bounded linear operators. With this, we are now going to study some further properties on convergence of a sequence of bounded linear operators.
We shall now discuss on strong convergence and weak convergence and uniform convergence of a sequence of bounded linear operators. Now we take some definitions. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital K. Let sequence Tn belongs to BD Lxy. That means BD Lxy is the collection of all bounded linear operators from x to y, and let T belongs to BD Lxy. Then Tn converges to T in norm if for every epsilon greater than 0 there exists a positive integer capital N such that norm Tn minus T is less than epsilon for all n greater or equals to capital N. Let us take another definition. let sequence Tn belongs to BDL xy and let T belongs to BDL xy, then Tn converges to T weakly, written as Tn goes to T weakly if for all x belongs to capital X, Tnx converges to Tx weakly. That means for every y dash belongs to capital Y dash Tnx converges to Y dash Tx. The sequence of bounded linear operators Tn belongs to BDL xy is said to be strongly convergent if for every x belongs to capital X, sequence Tnx converges in Y. Let sequence Tn belongs to BDL xy and T belongs to BDL xy, then Tn is called strongly convergent to T, that is sequence Tn is called strongly convergent to an element capital T if for x belongs to capital X, the sequence of elements Tnx converges to Tx and we write Tn converges to T strongly. Note that norm convergence of a sequence of operators Tn belongs to BDL xy to T belongs to BDL xy implies is strong convergence, because norm Tnx minus Tx is equal to norm Tn minus T into x, which is less or equals to norm Tn minus T into norm x, which goes to 0 as n tends to infinity. Let us take a definition. Let sequence Tn belongs to BDL xy and let T belongs to BDL xy, then sequence Tnx converges to Tx uniformly for all x belongs to capital X such that norm x less or equals to 1 if for every epsilon greater than 0 there exists a positive integer capital N such that norm Tnx minus Tx less than epsilon whenever n is greater or equals to capital N, written as Tnx goes to Tx uniformly. Alternatively, we say uniform convergence of a sequence of bounded linear operators Tn belongs to BDL xy in norm x less or equals to 1, written as Tn converges to T uniformly. If sequence of elements Tn belongs to BDL xy be such that sequence of operators Tn belongs to BDL xy uniformly for all x belongs to capital X satisfying norm x less or equals to 1, then Tnx converges to Tx uniformly for all x belongs to capital X with norm x less or equals to 1. The proof looks like this. Now, norm Tnx minus Tx equal to norm Tn minus T into x less or equals to norm Tn minus T into norm x. Let x belongs to capital X such that norm x less or equals to 1. So, norm Tnx minus Tx goes to 0 as n tends to infinity, implying that Tnx converges to Tx uniformly for all x belongs to capital X satisfying norm x less or equals to 1. Let us take another theorem. If sequence of bounded linear operators Tn belongs to BDL xy and capital T belongs to BDL xy be such that Tnx converges to Tx uniformly for all x belongs to capital X such that norm x less or equals to 1, then Tn converges to T in norm. The proof goes below. Let x belongs to capital X be such that norm x less or equals to 1. So, for any epsilon greater than 0 there exists a positive integer capital N belonging to set of natural numbers n such that norm Tnx minus Tx less than epsilon whenever n is greater or equals to capital N. Let us take an element y equal to x by norm x where x is not equal to 0 vector. So, norm y equal to 1. So, Tny goes to Ty uniformly implies norm Tny minus Ty less than epsilon for all n greater or equals to capital N. This implies norm Tn x by norm x minus T x by norm x less than epsilon for all n greater or equals to capital N. This implies norm Tnx minus Tx over norm x less than epsilon for all n greater or equals to capital N. This implies norm Tn minus T into x less than epsilon into norm x for all n greater or equals to capital N. So, supremum of norm of Tn minus Tx and supremum is taken over all such elements having norm x less or equals to 1, this less or equals to epsilon for all n greater or equals to capital N. So, norm Tn minus T less or equals to epsilon for all n greater or equals to capital N, implying that Tn converges to T in norm. Let us take a theorem. Let sequence of bounded linear operators Tn belongs to BDLXY and let T belongs to BDLXY. If Tn converges to T strongly, then Tn converges to T uniformly. Let Tn converges to T strongly, let epsilon greater than 0 be arbitrary. So, there exists a positive integer capital N such that norm Tn minus T is less than epsilon for all n greater or equals to capital N. Let y dash belongs to capital Y dash. Take x belongs to capital X, where y dash is the collection of all bounded linear functionals over y. Now, modulus of y dash Tnx minus y dash Tx equal to modulus of y dash Tnx minus Tx, which is less or equals to norm y dash into norm Tnx minus Tx, which is again less or equals to norm y dash into norm Tn minus T into norm x, which goes to 0 as n tends to infinity. This implies that y dash Tnx converges to y dash Tx. This implies Tnx converges to Tx weakly. This implies that Tn converges to T weakly. Thus, we have uniform convergence in norm x less or equals to 1 implies non-convergence. That means it's strong convergence. This implies weakly convergence. In this connection, we take a remark, but weakly convergence of sequence of bounded linear operators belongs to BDLXY does not imply its non-convergence. For this, we cite an example. Let x equal to small l2 define Tn from x to x by Tnx equal to 0 0 0 comma xi n plus 1 comma xi n plus 2 comma dot dot dot, where x equal to xi 1 comma xi 2 comma dot dot xi n comma dot 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 belongs to L2. Clearly, for each positive integer n, Tn is linear. Now, norm Tnx equal to sigma I equal to n plus 1 to infinity modulus of xi I square to the power half, which is less or equals to sigma I equal to n to infinity modulus of xi I square to the power half, which is equal to norm x, implying that Tn belongs to BDLXY. Since sigma I equal to 1 to infinity modulus of xi I square is finite, this implies that xi n goes to 0 as n tends to infinity. So, Tnx equal to 0 0 0 up to 0 up to nth place 0 comma xi n plus 1 comma xi n plus 2 comma dot dot dot, this goes to all coordinates 0, which is equal to 0 vector as n tends to infinity. Hence, Tn converges to 0 operator weakly on x. Let us take an element x equal to up to nth place 0 comma xi n plus 1 comma xi n plus 2 comma dot 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 belongs to L2 such that norm x less or equals to 1. Then Tnx equal to x. So, norm Tn equal to 1 for all n, but norm Tn minus 0 operator equal to norm Tn, which is equal to 1, implying that Tn does not converges to 0 operator in norm. So, by previous theorem, it follows that sequence of bounded linear operators Tn does not converge uniformly to the 0 operator.
Up to this, in this module, we have learned convergence of a sequence of elements in a nonlinear space. Also, we have learned some properties on convergence of a sequence of bounded linear operators. We have learned non-convergence, weak convergence and uniform convergence of a sequence of bounded linear operators. We have studied some properties on convergence of a sequence of bounded linear operators. With this, we now come to an end of this module 3 of chapter 8.